Welcome back everybody. We have left off in threads 1, and I would suggest we dive into it directly. So let's see, we have here two use statements, thread and duration from the time module. And over here in the main function we have a mutable variable handles which holds an empty vector. So as you can see, we can write it like that, or I personally like this syntax a little bit more, but it's both the same. Then over here we have a for loop, and it's iterating 10 times from 0 to 9. And in the for loop we are spawning a thread. And as you can see, this is happening in each iteration. So we basically have 10 threads. And we use the move keyword over here because we want to capture the environment variables. And as you can see over here, we use the thread sleep. So this thread will sleep for 250 milliseconds. And here you can see that's why we have imported the duration type over here. And then we just print out thread number so and so is complete. Then over here after the for loop we have a mutable reference, once again completed threads, which is 0. And then we again have a for loop for handle in handle, so that's basically this vector over here, and it just increments this variable by 1 each time it iterates over a handle in the handles variable in this vector. And if completed threads is not equal to 10, this line will get printed and the program will panic. All right. So as you can see over here, we have an empty vector and the type inside the vector is unknown. So we have to change that. And what we basically have to do over here is to do a struct is returned from thread spawn. Can you use it? So as you know, thread spawn will return a join handle. That's a struct. And this struct allows us then to use the keyword join. And join allows us to iterate or basically run all the threads and keep them running until every thread is finished. So over here we can then use or in line 16 we can push this thread into the handles. So we can call handles push, and then over here we have thread spawn like that. And as you can see now in the vector we have a type join handle, and that's basically a struct we can then use to call upon it the join method. So handle, we can then do it like that, and join will return a result, as you can see here. And that's why we will then unwrap it like that. And as I've said, join basically makes sure that all the threads finish executing. So every thread can finish its execution. Let's see. And as you can see, the code is compiling, and you can see thread 4 is complete, thread 3 is complete, thread 0. And again, we are here handling multiple threads. So every thread is running concurrently, that means independently, and in parallel, meaning all threads run at the same time, and that's why some of them complete before other ones. So in this case, thread 9 was the slowest one to complete, and thread 4 was the fastest one. And we have used join over here just to make sure that every thread runs completely. So as you can see, we have from 0 to 9 every thread in here that completed its execution. All right, let's see the next one. Okay, we are here importing arc and thread and duration again. And over here we have a struct job status with a member jobs completed of type unsigned integer. So let's see, we have here a variable status that holds our struct, or basically initiates it with jobs completed 0, and it gets wrapped inside arc new. So this is then the type we have arc job status. That's this struct. And as I've said, it's covered inside arc. Then again, we have a variable which is mutable handles, which holds an empty vector. Again, I will do it like that. And over here, basically the same thing. We have a for loop that iterates 10 times from 0 to 9. And this underline over here basically is just a placeholder. If you don't need this variable over here, for example, I or anything you want, you can just place an underscore, and that means you won't use this variable inside the code in the for loop. And then we have here status shared, and we clone this status variable, and we again have a spawn thread, or basically we spawn threads every iteration in the for loop. Again, we move the environment variables inside the capture, and this thread, or every thread in this for loop iteration, will sleep for 250 milliseconds. And then status shared jobs completed gets incremented by 1 in each thread inside this iteration, and then we push this handle inside this vector handles, which holds types of join handle. And then again, as in the last exercise, we have here a for loop, and it basically just, here we have the join method. So this makes sure that every thread runs until it's completed, and unwrap because join returns a result. Okay. Now, as you can see, we have here expected expression, so we have to fill that one out. Print the value of the job status, jobs completed. Did you notice anything interesting in the output? Do you have to join on all the handles? So And here you must take an action before you update a shared value. So this is the keyword over here, shared value. We want to share this value over here with all the threads that are running inside here. And every thread can modify this value inside here. And that's what we call shared state concurrency. What this basically means is you have a state, and for example, we have here an integer 5. This is a state, and then you put it into mutex, and this then allows you to share this state with all the threads, and you can then mutate it. As you can notice, this actually isn't mutable, but mutex allows the threads to mutate the state safely. So a mutex is basically wraps a state value you want to make mutable inside the threads, but for the outside you want to leave it immutable, like that. And for it, or for you to be able to access it, we have to first attain a lock. So you can call a lock method on a variable that holds a mutex type, and again this will return result type, so we have to unwrap it. And this actually returns a smart pointer which is called mutex guard, and this is wrapped inside lock result. That's just the name. It's basically like a normal result type, and that's the reason we have to call upon it unwrap. And when we have attained the lock, then we can mutate the state inside the mutex. So as you can see, we then dereference it because the mutex guard has the deref trait enabled on it or implemented, so you can without problem then dereference it and assign it a new value. And also it has the drop implementation. That means if the variable that holds the lock will get out of scope, then the lock is basically freed. So that releases the lock automatically when a mutex guard goes out of scope. So this holds then a type of mutex guard, and as you can see, after this scope ends, then the lock over here will get freed, so other threads can use it. And this lock basically means every thread or every variable that wants to access mutex type has to attain it through a lock. And this is basically to make sure that only one that the variable inside the mutex gets modified only once before the lock will get released back. So it's not possible that a program can modify the value in the mutex multiple times. And as you know, in threads, every thread runs in parallel, so we would have a problem if every thread tries to modify the value inside there, because that would mean a data race, and this would basically confuse the program and you would get errors or undefined behavior out of that. So this basically makes sure that every time you want to modify something in mutex, you first have to attain the lock and then again free it or drop it. So let's see, or I have here mutex. Let me zoom in here. Mutex is another way to change values without declaring mute. Mutex means mutual exclusion, which means only one at a time. This is why a mutex is safe, because it only lets one process change it at a time. Right. To do this, it uses lock. Lock is like locking a door from the inside. You go into a room, lock the door, and now you can change things inside the room. Nobody else can come in and stop you because you locked the door. That's basically what I tried to explain. Of course, this is much more precise. So mutex allows for mutability, but only one process at a time can change the value inside mutex. So what we want to do over here is we want to do this inside mutex, and I see we didn't import it, so let's import it over here. We have here arc and mutex, like that. And this is from the sync module. Then over here, we can do mutex, new, and then inside we can wrap it like that. And as you can see, we have then job status wrapped inside mutex, wrapped inside arc. And arc basically just allows us to share ownership between various different processes or threads in this case. So what we then can do is, as you can see, we are cloning the status over here. So basically, as you saw in the book, we have to first attain a lock to be able to mutate a value. So that's what we do over here. We attain a lock and then we unwrap it. We attain a lock and then unwrap it like that. And then we can basically access jobs completed inside the struct and increment it by 1. And that's basically what we needed to do over here. Now over here we have to print it out, and again we are then iterating over handle in handles. So that's this vector which holds join handles. So what we want to do here is we want to access the jobs completed again and print it out. So what we then can do is we get the status, that's this variable over here, and again, because it's of type mutex inside arc, we have to attain a lock. So every time you have a mutex, you always have to attain a lock before you can do anything with it. And then, as you can see, we can access jobs completed like that. And this should actually work. And as you can see, it's compiling. And here you see jobs completed 4, 4, 6, 6, 9, 9, 9, 9, 10. So let's save it again, just nice to see. All right, as you can see, jobs completed. Every job is completed. That basically means that in every thread we spawn over here, we have 10 threads. In every thread, it gets incremented until it reaches 10. As you can see, because in each iteration it iterates 10 times, and in each iteration it increments by 1. So each thread then has a value inside of 10. Inside this struct, jobs completed, in every thread we have 10. And that's why we use mutex, because as you can see, we have shared a state. This is here the state we want to share with every thread over here. And we have shared it with every thread, and we have modified its value from every thread. All right. And I guess the last one. Okay. Let's see. Threads 3. Okay, I got the problem over here. Let me just reset this. Threads 3. Okay. Now I want to go outside Vim. And we exit from here too. So let's see. I go inside Rustlings. Threads 3. Okay. Let me open a new terminal. Threads 3. Okay, we can modify it anyways. So what's happening? Okay, like that. All right, so as you can see, we have here imported MPCC, and this is a module which stands for multiple producers, single consumer. And I will come back to that. We have arc, we have thread, and duration. Now here we have a struct Q, which holds length of type unsigned integer, first half, and second half, both of type vector unsigned integer. Now we also have a method for Q, which is new. It will just return a Q. Self here means just the type we are implementing this method on, which is Q. So all this method does is we can run new, and then we will get back a Q with length of 10 and a vector 1 to 5 and a second vector 6 to 10. And then over here, as you can see, we have a function send, and this TX stands for transmitter. And we have Q, which is of type Q, and a transmitter. And this is of type MPSC sender, and it sends an unsigned integer. Now over here we have QC, which is arc new Q. So we take this Q and wrap it inside arc. So we want here to share ownership. Let me zoom out just a little bit. Then we have QC1, which just clones QC, which clones, yeah, QC, that one. And we have QC2, which just clones QC again. So we basically have this argq, and here it gets cloned 2 times. Now actually, let me also change that in the last one. We had here threads 2. Now over here, as you can see, we had here clone, status clone, but we can actually clone it like that, and that's even better. Status like that. And Rustlings watch. Because this allows you to clone without making a deep copy. So this program will use less overhead, because you're not making a deep copy, you're not copying this status, everything in it inside memory. You're just basically creating a new pointer to this location in memory. Like that. And I just want to make sure it compiles. Yes, we are inside threads 3. So threads 2 is compiling, and I will go out of here. And let's continue. So as you can see, we can clone it basically, but this will make a deep copy of this queue, and that's not what we want. We want it to use arg clone, because we have here archetype, so we use clone on it, and QC, and over here basically we just copy this, paste it here like that. All right, now over here, as you can see, we are spawning a thread. We are using the move keyword, so these values get moved inside over there. And we have a for loop, so we are iterating over this vector QC1, which holds this 1, 2, 3, 4, 5. And as you can see, we are iterating over references of unsigned integers. So then we are printing out these values, and then we are sending it. So here you use tx, which is transmitter, and we send it. We send this value, and of course, because it's a reference, we have to dereference it. And then unwrap, because send will return a result type. And as you can see, this thread sleeps for 1 second. And the second thread over here does basically the same thing. We are accessing QC2. This is the second clone of QC. And we are printing out the value and then send the dereferenced value through tx.send. And tx and rx, as you can see in the main function, is a tuple which gets returned when we use MPSC channel. So you open a new channel over here, which then allows you to use these two variables, tx and rx. tx for transmitter and rx for receiver. So then we create a new queue. As you can see, we are using here the new method that's implemented over there. So we get back a queue with these values over here. And then queue length. So we just have a length over there. And that's basically this one. Queue length, we will put it inside a separate variable. And then, as you can see, we are calling this function over here. That's this one. And we pass it a q and the tx. As you can see, this q we have created over here, we pass it, and the second argument is tx of type sender. And as I've said, tx stands for transmitter, so it is of type sender. And then we have here a mutable variable, total received, which starts at 0, and then for received in Rx. So with Rx, let me basically just show you that. Using message passing to transfer data between threads. So the first exercise we have done was with mutex, and this allows you to have a state which is shared between threads, and you can mutate this state, and this state is constantly available. Now there is another approach using message passing, and message passing basically is you have in each thread some calculations you will do and processes, and then you can basically send it to another thread, and then the thread receives it and does something with it. So as you can see, this is what I've shown you. We use MPSC, which stands for multiple producer, single consumer, and we call the channel method on it, and then we get back a tuple transmitter and receiver. Now multiple producer, single consumer basically means that you can produce as many of these TX as you want, but there is only one receiver. That's basically what that means. In short, the way Rust standard library implements channels means a channel can have multiple sending ends that produce values, but only one receiving end that consumes those values. That's what this means. And then, as you can see, we have here a thread, and it has a variable which holds a value, and then we are sending this value through tx, which we attained through the method channel. And then we can use send method to send it to Rx. And then, as you can see, we can use Rx, the received method, and then we can just do something with the received value we got from this thread. So in this case, we are just printing it out like that. And maybe you're asking now, I didn't see this receive function in the exercise. So when you're using a for loop, you don't need that. You don't need to write like that. I think you even could, but it's not necessary. So you just can iterate directly over Rx. So this is not necessary. And yeah, that's basically what I wanted to show you. Now, as I've said, we can have multiple transmitters or producers. That's this MP, multiple producers. So we can have many TXs like that. And as you can see, we have here the first one, or basically here tx send, and it sends all of these. And here we have another one, tx1, which sends another one down to the receiver Rx. So as you can see, what we basically did is we have a tx and we just clone it like that. So, and what we need to do over here, as you can see, move occurs because tx has type sender, which does not implement the copy trait. So what we want to achieve over here in the send tx is basically just to, we have multiple tx's we want to use. So as you can see, we are here tx send and tx send. So we have multiple producers, and that means all we have to do is really make tx1 like in the book, for example, and we take this tx and we clone it like that. And as you can see, we then have a clone, and then we can use it over there. So tx1. And as you can see, it is compiling. So we needed to do that because as we've seen in the book, we have to clone the tx. The tx can be used once only, and the rest we have to clone it like that. And also maybe something important, when you send down something, for example this value then cannot be used anymore. So if I try to print, let's just make it like that, val, we will get a compile error. Alright, in this case we don't get a compile error, of course, because we are using arc, which allows us to have multiple ownership. But as you can see over here, we have val and we are sending it down. So when we try to access val once again, we will get a compile error. This won't compile. As you can see, borrow of moved value. But of course we can use arc, which allows multiple ownership like we have over here. So this is no problem. All right, I think that's all that needs to be said. Yeah, I think we're done. And let's see the next topic. And the next topic will be macros. See you then.